Welcome to AI Paper Slop, where we summarize the latest AI and tech papers for you. You know, the technical folks, the AI researchers, ML engineers, and developers looking to stay on the bleeding edge.
Yeah, we like to get right to the point here.
Exactly. So today we are diving straight into a paper that basically dismantles how we currently train robotic models. It's called LA4VLA, Learning to Act Without Seeing via Language Action Pre-Training.
Right, from researchers at Shanghai Jiaotong University, Alibaba Group, NTU, and COST.
And here is your 60-second core insight. Current vision language action models, or VLAs, are fundamentally broken.
Fundamentally.
Yeah, because dense visual data completely overwhelms sparse language instructions during training. The models just learn visual shortcuts instead of actually following your text commands.
Which is a huge problem when you deploy them.
Right. So the researchers introduce a pretty radical fix. They explicitly remove vision during a new pre-training phase. They take expert trajectories, break them down into about 33,000 atomic action segments, and pair them solely with language and proprioceptive state data.
And that forces the model to learn pure language action priors.
Yeah. Exactly. And the outcome is just staggering. They took a lightweight 1 billion parameter model, and its success rate on real-world physical robot tasks jumped from roughly 38% to 83%.
That is massive.
Right. Plus a massive improvement in its ability to handle visual noise.
I mean, we spend an incredible amount of engineering effort trying to figure out how to feed, more high bandwidth multimodal data into our architectures.
Oh yeah, everyone just wants more data, more modalities.
Exactly. The prevailing logic right now is that more modalities equal better representations. But what this paper proves is that when you're trying to establish a fundamental mapping between a text token and a motor action, feeding the model high-definition video is actually, well, it's toxic to the learning process.
Toxic?
Yeah, you basically have to temporarily starve the model of vision to force it to learn the underlying logic.
Okay, let's unpack the mechanics of that toxicity, because we really need to understand exactly why standard VLAs are failing before we look at the cure.
It really comes down to a severe asymmetry in the training data pipeline.
Right. Picture standard joint VLA training. You feed the network a single high-level language instruction. It might be, 10 or 12 text tokens specifying an overall task goal. Something simple like clean the table.
But look at what those 10 language tokens are competing against inside the architecture. That one sparse instruction is paired with hundreds, sometimes thousands of dense, dynamically changing image action pairs across the whole trajectory.
Because it's processing video frames.
Exactly. At the model input level, you are encoding visual observations into hundreds of image tokens per frame. From a purely mathematical standpoint, the image tokens outnumber the language tokens by orders of magnitude.
So the loss function is going to heavily prioritize the data stream that carries the highest variance, right? And the most immediate correlation to the required output.
Which is the visual stream, always.
Yeah, if you're a neural network optimizing for a loss function and you have this massive, rich stream of visual data that correlates perfectly with the actions you need to take, and then just this tiny little text string on the side, you're going to use the visual data.
It would be stupid not to, mathematically speaking.
Exactly. It's like a student who memorizes the visual layout of a multiple choice test instead of, actually learning the physics equations.
Oh, that's a great analogy.
Right. They know that on page 3, the answer is usually C because the paragraph above it looks a certain way. But the moment you shuffle the questions, or in the robot's case, change the visual background, they completely fail.
The language is just a weak suggestion to the model at that point.
Yeah.
It isn't driving the behavior at all.
Right. And the researchers actually proved this multiple choice phenomenon with a highly controlled diagnostic study.
They did. They used an intern VL31B model as their baseline. And just to provide some context on the architecture for you, this is a relatively lightweight 1 billion parameter vision language model, and they equipped it with a flow matching action head.
Right, and for those who might not be deep into motion generation, a flow matching action head essentially means the model isn't just outputting discrete step-by-step positions.
No, it's learning to predict the continuous fluid motion trajectories of the robot's joints.
Exactly, which makes it highly sensitive to the inputs it receives.
So they trained this specific architecture on standard VLA data and then tested its ability to follow atomic directional commands, things like move upward.
Simple stuff.
Yeah. But the experimental design here was really clever. They kept the language instruction completely constant, but they intervened on the visual inputs.
Okay, so what happened when they used the standard paired input, like the image that actually belonged with that specific upward trajectory?
The model performed flawlessly, as you'd expect. They measured this using two metrics. First, the directional alignment rate, or DAR, which hit 0.98.
Which is practically perfect.
Yeah. And second, the direction consistency score, the DCS, which measures the cosine similarity between the predicted movement vector and the ground truth vector. That hit 0.95.
So on the surface, the model looks like a perfect instruction follower.
Right, until they pulled the rug out. They tested a visual removed condition where they just masked the image entirely.
And performance instantly collapsed, didn't it?
Oh, totally. The DCS dropped from 0.95 all the way down to 0.16.
Wow.
But the most damning evidence came from the visual conflict input.
This is the part that really got me.
Yeah, they fed the model the text instruction to move upward, but they swapped the visual feed with an image observation that was originally associated with moving downward.
So the text explicitly says go up, but the visual context implies the action is going down.
And the image wins by landslide. The direction consistency score plummeted to 0.03.
Well, that's crazy.
And the directional alignment rate dropped to 0.35.
Yeah.
We should know for you guys listening, a DR of 0.5 is literally random guessing.
Right, so a 0.35 means the model is actively moving in the wrong direction.
Exactly. It completely ignores the text command and follows the visual shortcut. The language action grounding is a total illusion.
Okay, wait, I have to ask though. If the diagnosis is that visual data is acting as a crutch, and the solution is to take the crutch away during pre-training, how does the robot learn spatial awareness?
What do you mean?
Well, if I completely blindfold you, you can't navigate dynamic obstacles or grab a coffee mug. Doesn't completely blinding a neural network ruin its ability to understand the geometry of the physical world?
That is the exact trap most researchers fall into. They assume you need vision at all stages of training.
Right, because it intuitively makes sense.
Sure, but the key insight of LA4VLA is separating the prior from the deployment. You aren't permanently blinding the robot.
Oh, okay.
You're using a visionless pre-training phase strictly to burn the language action mapping into the model's weights. You are teaching it what the concept of up, grasp, and push physically feel like in its own joints, its proprioception, before you ever let it see a camera feed.
I see. So once that deep logical mapping is established, you reintroduce vision during the fine-tuning stage.
Exactly. And then the model uses the camera for precise spatial targeting, rather than using it as a crutch to replace language.
Okay, so logically, we need a data set to teach it these concepts without vision. But you can't just take a standard long horizon trajectory, mask out the video, and expect a model to learn anything useful.
No, definitely not.
Right, because if you feed a blind model a command like clean the table, paired with 300 frames of complex meandering arm movements, that's just unlearnable noise.
Complete noise. You need highly specific atomic language action data.
And building that data set is where the pure data engineering muscle of this paper really shines. They built this massive pipeline without collecting a single new robot trajectory.
Yeah, they repurposed the existing DROID dataset by mining the implicit signals already hidden inside it.
And the DROID dataset is a beast. It's this massive collection of real-world robotic manipulation data, but it is incredibly messy.
Very messy. They started with about 9,500 original long horizon VLA episodes from DROID, averaging about 287 frames per episode.
So to chop these long, complex operations and learnable atomic actions, they utilized keyframe detection, which makes sense in theory, but how do you mathematically define a keyframe for a robot arm that is constantly in motion?
It's tricky.
Yeah. What constitutes the end of one atomic thought and the beginning of another?
Well, they looked for two very specific physical state changes in the proprioceptive data.
Okay.
First, static keyframes. These are moments where the arm state variance drops near zero.
Because it stopped moving.
Exactly.
Right.
In real-world physics, when a robot stops moving its joints, it usually indicates it has finished an alignment phase and is transitioning to a new subtask.
Makes total sense.
And second, gripper transition keyframes. These are the exact frames where the gripper state flips from open to closed, or vice versa.
Oh, that's smart. Because mechanically, a gripper closing is the perfect boundary for an atomic action. It represents a completed intention the robot has reached the object and secured it.
Right. So they use those physical state boundaries to chop the 287 frame trajectory into tiny, discrete chunks.
But a chunk of movement still needs a text label.
Yes, and to get those, they pass these segments into a vision language model, specifically Qwen 3 VL+.
Okay, Qwen 3.
They prompted the VLM to analyze the video chunk alongside the keyframe hints and output two things: a primitive label, like grasp, lift, push, or reorient, and a vision-agnostic instruction.
Forcing the instruction to be vision-agnostic is such a subtle but critical design choice.
Yeah, right.
Because the VLM couldn't generate a label like pick up the red apple because during this specific pre-training phase, the robotic model won't have a camera feed. It won't know the object is a red apple.
Exactly. The text had to focus entirely on the physical kinematics, something like lift the object vertically upward while holding it.
But relying purely on VLM-generated labels for a physical robotics policy is usually a recipe for disaster.
Oh, 100%.
Yeah.
Hallucinations in the training data will completely ruin the policy.
Right, and the authors knew this, so they introduced a rigorous human verification step. Annotators reviewed the VLM proposals, checking if the temporal boundary, the action label, and the text instruction were all perfectly aligned.
And they achieved a Krippendorff's alpha of 0.7794.
Yeah, and for the engineers listening, Krippendorff's alpha is a statistical measure of inter-rater reliability. A score approaching 0.8 essentially means the human graders independently agreed with each other a very high percentage of the time.
So the quality of the labels wasn't just random luck or subjective guessing.
Exactly. It's solid data.
And the output of this entire pipeline is this pristine data set they call LA33K. It contains over 33,000 episodes.
The average frame count per episode dropped from 287 down to just 46.
Which is much more manageable. But most importantly, for these 33,000 episodes, the visual data is completely discarded.
So they managed to convert sparse, high-level task language into dense, localized language action supervision. So now we have the LA33K dataset. The next question for the developers and ML engineers listening to this deep dive is implementation. How do you actually schedule this pre-training to inject the knowledge into the model?
Right, so the author set up 5 specific training paradigms on their 1 billion parameter model to figure out the optimal architecture flow.
5 paradigms. Let's run through them.
The 5 paradigms allow us to isolate exactly where the performance gains come from. First is base, which bypasses pre-training entirely and just does standard fine-tuning on the downstream tasks.
Okay, standard baseline.
Second is VLA, which is pre-training on the newly created atomic segments, but keeping the visual feed enabled.
Got it.
Third is the core proposal, LA, which is pre-training on the segments with zero vision, just language, proprioception, and action.
A blind pre-training.
Yes. Fourth is LAVLA, a sequential approach where they do LA pre-training first, followed by a stage of VLA pre-training.
And finally,
mix PT, where they mix the blind LA data and the visual VLA data into a single combined pre-training stage.
Okay, so they took these paradigms into simulation, testing them across the MetaWorld and Libero benchmarks. And the numbers provide definitive proof of their hypothesis.
They really do.
On MetaWorld, the base model with no pre-training managed a 69.7% success rate. If you do standard VLA pre-training, keeping the vision on it improves to 79.7%.
Which is a decent jump.
It is, but if you execute LA pre-training, completely blinding the model to force the language prior, the success rate climbs to 83.0%.
Think about the implications of that result for a second. Simply by withholding visual context during pre-training, the model outperforms an identical architecture that had access to the full visual scene.
It's wild. And when they combine the modalities, MixPT took the absolute crown on MetaWorld, reaching an 87.53% success rate.
And this technique isn't isolated to their specific intern VL3 architecture either.
Right. They applied this exact LA pre-training methodology to Star VLA, which is a fundamentally different model, and witnessed an 11.52-point jump on MetaWorld.
Which really proves LA pre-training is a highly transferable regularization technique.
It is highly transferable, but if you look closely at the data between the sequential training and the mixed training paradigms, a fascinating nuance emerges regarding deployment strategy.
Oh, for sure.
If you're an engineer building a deployment pipeline right now, you're probably wondering which of those two combined paradigms to choose. Like, why did MixPT dominate MetaWorld while LAVLA actually edged it out on the Libero benchmark?
It's a great question.
Does sequential training cause catastrophic forgetting of the language prior, or is there something fundamentally different about those simulation environments?
It actually appears to be heavily dependent on the visual complexity and horizon of the task, rather than catastrophic forgetting.
Okay, break that down.
Well, MetaWorld tasks often require a very tight, immediate coupling between the spatial visual features and the action, which a mixed training approach handles beautifully because it learns to balance the modalities simultaneously.
Ah, I see. And Libero.
Libero features much longer horizons and significantly more complex visual distractions. In that environment, LAVLA logging in an unshakable language action foundation first, before ever introducing the messy visual data, proved slightly more robust.
Right, hitting 96.28% versus MICPT's 95.75%.
So both staged and mixed integration work, but your choice depends on the visual noise of your target environment.
So simulation benchmarks are great for iteration, but deploying a 1 billion parameter model to physical hardware is the real crucible.
And the physical deployment is where the paper really solidifies its claims. They utilized an ASARM-6 robotic manipulator equipped with a parallel jaw gripper.
And they evaluated it across 3 language condition tasks, right? Press button, place book, and place drink.
Yep. And they only collected 100 teleoperated demonstrations per task.
Which is not a lot of data.
Not at all. But the genius of this physical evaluation lies in the experimental design of the tasks themselves.
They intentionally designed identical starting frames.
Exactly. Take the press button task. There are 4 identical buttons arranged on the table. When the episode starts, the visual frame captured by the camera is entirely static and identical, regardless of which button needs to be pressed.
So the visual observation contains 0 mutual information about the target goal.
None. The robot has absolutely no visual cues to rely on. It must parse the language command like, press the top right button to successfully complete the trajectory.
And parallel jaw grippers are incredibly unforgiving. If the policy is even slightly off in its spatial understanding, the gripper will just deflect off the button or knock the book over.
Oh yeah, they are brutal.
And the physical results mirror the simulation, but the delta is far more extreme. The base model managed a dismal success rate of 38.3%.
Terrible.
Standard VLA pre-training with vision enabled bumped that to 48.3%, but the LA pre-trained policy skyrocketed to 81.7%.
And mixed PT hit 83.3%.
I mean, we were looking at a 45 percentage point increase in real-world reliability simply by changing the formatting of the pre-training data.
It's incredible. And the authors took it one step further with a stress test that mimics the reality of industrial deployment.
Because in the real world, camera sensors degrade, lighting changes, lenses get dirty.
Exactly. So they took those fine-tuned real-world policies and intentionally injected Gaussian image noise directly into the visual feeds during execution.
They degraded the cameras with a standard deviation of 5 for the button task and 15 for the drink task.
And as anticipated, the base model, which learned to lean heavily on high-fidelity visual features, completely shattered. Its success rate plummeted to 27.5%.
Ouch.
But the MICPT model held remarkably strong, maintaining a 70% success rate despite the degraded vision.
Which just shows LA pre-training is acting as a profound regularization mechanism here. By forcing the neural network to deeply internalize the mathematical mapping between its own proprioceptive states, specific language tokens, and physical geometry first, it establishes a structural understanding of the task.
Right.
So when the visual feed gets noisy, the policy doesn't panic and output random motor commands because it has a foundational logic to fall back on.
And we don't just have to theorize about that structural understanding either. The authors actually visualized it by looking inside the network's latent space.
Oh, this is the TSNE part.
Yeah, they ran a TSNE clustering analysis on the policy representations extracted right before the action decoding layer.
We should probably quickly define TSNE for context. It's a visualization technique, basically a mathematical way to take the high-dimensional thoughts of a neural network, which might exist across thousands of parameters, and compress them down into a 2D scatter plot so human researchers can actually see how the network is organizing concepts.
Exactly. And when you look at the TSNE plot for the standard VLA trained policy, it is chaotic.
Chaotic is a good word for it.
The representations form scattered, overlapping clusters that are grouped almost entirely by the robot's physical coordinate state. The language instruction barely influences the latent space at all.
So if you command the robot to move forward or move left, those representations are basically just jumbled together into the same visual cluster.
Yeah.
It looks like a hoarder's closet where everything is just thrown in based on whatever object was nearest at the time. There is no logical organization.
None. But when you run that same TSNE visualization on the LA pre-trained policy, the space transforms into an organized filing cabinet.
A filing cabinet, I like that.
The representations form beautiful, distinct clusters that are explicitly categorized by the commanded directions. The latent cluster for the action move forward is entirely cleanly separated from move right or move backward.
And that visualization proves the policy is making its fundamental decisions based on the text structure. It has successfully internalized the geometry of the language commands, completely independent of the visual shortcuts it used to rely on.
The text is no longer just a weak conditional input. It is the primary driver organizing the action space.
Which is exactly what you want. So to summarize the core takeaway for the researchers and developers listening to this deep dive, vision is undeniably necessary for fine-grained object localization and scene-specific targeting during deployment.
You definitely still need cameras.
Right. But during the foundational pre-training phase, high-bandwidth visual data acts as an overpowering crutch that prevents the model from learning to actually follow instructions.
Yes, the data is too rich.
So by intentionally blinding the VLA model and forcing it to learn atomic language action pairs through the LA4VLA framework, you permanently cure the architecture of its visual over-reliance. The final policy exhibits vastly superior instruction following fidelity and is immensely more robust when deployed into the messy, noisy physical world.
And honestly, the findings in this paper present a philosophical challenge for how we build multimodal systems moving forward. Well, if intentionally starving an AI model of its richest, highest bandwidth data modality forces it to construct stronger, more robust underlying logical representations, what does this mean for our broader pursuit of generalized agents?
Well, that's a good point.
Are we inadvertently making our audio-visual models fundamentally brittle by drowning them in massive data streams from day one? Perhaps to engineer true generalized intelligence, we need to teach our architectures to close their eyes more often.
The student memorizing the multiple choice test eventually has to close the book and actually learn the physics equations.
Exactly.
Well said. Thank you for joining us for this analysis of the LA4VLA paper here on AI Paper Slop. To the technical community out there, keep building, keep experimenting, and we'll catch you on the next deep dive.